It is required to have protection between the transformer and the automatic transfer switch because of protection from short circuits. The protection device safeguards the transformer from any excessive current that may arise during a short circuit or overload condition in the downstream circuit. In the event of a fault in the automatic transfer switch or downstream circuit, the protection device isolates the transformer, preventing damage or further electrical disturbances. NEC Article 700.12b2 states that overcurrent protection shall be provided in each ungrounded conductor at the point where the conductor receives its supply. NEC Article 450.14b specifies that generators shall be equipped with overload protection. The protection device may be integral with the generator or provided externally. The protection device can typically be a circuit breaker or fuse. It should be selected based on the transformer's rating and the load demand. The specific requirements for protection between the transformer and the automatic transfer switch may vary depending on the local codes and regulations. It is recommended to consult with a qualified electrician or electrical inspector for guidance. To elaborate, let's delve into the technical rationale and code compliance considerations. The primary function of placing an overcurrent protective device, such as a circuit breaker or fuse, between the transformer and the automatic transfer switch, or ATS, is to protect the transformer itself from overcurrent conditions. These conditions can arise from various sources, including short circuits, overloads, or ground faults in the downstream circuitry connected to the ATS. A transformer is designed to operate within specific voltage and current parameters. Exceeding these parameters can lead to overheating, insulation breakdown, and potentially catastrophic failure of the transformer. The overcurrent protective device acts as a safeguard, interrupting the current flow when it exceeds the transformer's safe operating limits. A short circuit is an unintentional low-resistance connection between 2 points in a circuit that have different voltages. This results in a very high current flow, potentially thousands of amps, which can quickly damage equipment. The overcurrent protective device detects this rapid increase in current and trips, opening the circuit and preventing damage to the transformer, conductors, and other components. An overload condition occurs when the current drawn by the load connected to the transformer exceeds its rated capacity. This can happen due to excessive demand, malfunctioning equipment, or a combination of factors. While an overload may not cause an immediate failure, prolonged exposure to excessive current can overheat the transformer, degrade its insulation, and shorten its lifespan. The overcurrent protective device responds to the increased current by tripping after a certain time delay, preventing long-term damage to the transformer. A ground fault is an unintentional connection between a live conductor and ground. This can occur due to damaged insulation, accidental contact with grounded objects, or other unforeseen events. A ground fault can create a dangerous shock hazard and also cause damage to equipment. The overcurrent protective device, in conjunction with a grounding system, helps to quickly clear ground faults, minimizing the risk of electric shock and equipment damage. The National Electrical Code, or NEC, provides specific requirements for overcurrent protection of transformers and generators. NEC Article 450 addresses transformers, while Article 700 covers emergency systems, which often include generators and automatic transfer switches. NEC Section 450.3, which addresses overcurrent protection, is particularly relevant. This section specifies the maximum overcurrent protection allowed for transformers based on their voltage rating and impedance. The overcurrent protection must be sized to protect the transformer from both overload and short circuit conditions. NEC Section 700.12b2 mandates that overcurrent protection be provided in each ungrounded conductor at the point where the conductor receives its supply. This means that the conductors feeding the ATS from the transformer must be protected by an overcurrent device located at the transformer's secondary terminals or at the point where the conductors originate. This requirement ensures that the conductors are protected against overcurrent conditions that may occur downstream of the ATS. NEC Section 445.12 addresses overcurrent protection for generators. This section requires that generators be protected against overload. The overcurrent protection may be provided by a circuit breaker or fuse located at the generator's output terminals, or it may be an integral part of the generator's control system. The overcurrent protection must be sized to protect the generator from overload conditions without causing nuisance tripping during normal operation. The selection of the appropriate overcurrent protective device for a transformer and ATS application requires careful consideration of several factors, including the transformer's kVA rating, voltage rating, impedance, and the characteristics of the load connected to the ATS. The overcurrent protective device must be sized to protect the transformer from both overload and short-circuit conditions, while also allowing for normal load variations and inrush currents. Circuit breakers and fuses are the two most common types of overcurrent protective devices used in these applications. Circuit breakers are resettable devices that trip when the current exceeds their rating. They offer the advantage of being reusable, but they may be more expensive than fuses. Fuses are one-time devices that melt and open the circuit when the current exceeds their rating. They are generally less expensive than circuit breakers, but they must be replaced after each overcurrent event. The choice between a circuit breaker and a fuse depends on the specific application requirement and the owner's preference. In addition to the NEC requirements, local codes and regulations may also impose specific requirements for overcurrent protection of transformers and ATS. It is important to consult with a qualified electrician or electrical inspector to ensure that the installation complies with all applicable codes and regulations. Coordination studies are often conducted to ensure that the overcurrent protective devices in a power distribution system are properly coordinated. A coordination study involves analyzing the current time characteristics of all the overcurrent devices in the system to ensure that the device closest to the fault trips first, minimizing the impact of the fault on the rest of the system. A properly coordinated system improves the reliability and safety of the electrical system. In summary, providing overcurrent protection between a transformer and an automatic transfer switch is essential for protecting the transformer, conductors, and downstream equipment from overcurrent conditions. The NEC provides specific requirements for overcurrent protection of transformers and generators, and local codes and regulations may also apply. The selection of the appropriate overcurrent protective device requires careful consideration of several factors, and coordination studies are often conducted to ensure that the overcurrent devices are properly coordinated. Consulting with a qualified electrician or electrical inspector is recommended to ensure compliance with all applicable codes and regulations. Let's further clarify some key aspects. Firstly, consider the transformer nameplate data. This provides essential information for determining the appropriate overcurrent protection. The nameplate includes the transformer's kVA rating, primary and secondary voltages, impedance, and temperature rise. All of these factors play a role in selecting the correct overcurrent device. Secondly, calculate the transformer's full load current, or FLC. This is the current the transformer will draw when operating at its rated kVA and voltage. The FLC is used to determine the minimum ampacity of the conductors feeding the transformer and the minimum rating of the overcurrent protective device. Thirdly, determine the available fault current at the transformer's secondary terminals. This is the maximum current that will flow during a short circuit condition. The available fault current is used to determine the interrupting rating of the overcurrent protective device. The interrupting rating is the maximum current that the device can safely interrupt without failing. Fourthly, select an overcurrent protective device with an interrupting rating that is equal to or greater than the available fault current. If the interrupting rating is too low, the device may fail to clear the fault, potentially leading to equipment damage or personal injury. Fifthly, consider the type of load connected to the ATS. The type of load will affect the size and type of overcurrent protective device required. For example, motors and other inductive loads can draw high inrush currents when they start. The overcurrent protective device must be able to withstand these inrush currents without tripping. Sixthly, coordinate the overcurrent protective devices with other devices in the system. This is important to ensure that the device closest to the fault trips first, minimizing the impact of the fault on the rest of the system. Coordination studies are typically performed by qualified engineers. Seventhly, install the overcurrent protective device in a readily accessible location. This will allow for easy inspection and maintenance. Eighthly, label the overcurrent protective device clearly. This will help to identify the device and its function. Ninthly, inspect and test the overcurrent protective device regularly. This will help to ensure that it is functioning properly. Tenthly, maintain accurate records of all overcurrent protective devices. This will help to track their performance and identify any potential problems. Here is some additional guidance regarding specific NEC articles. Article 240 in the NEC covers overcurrent protection in general and provides requirements for the selection and installation of overcurrent protective devices. Article 450 provides specific requirements for the overcurrent protection of transformers. Article 700 covers emergency systems and provides requirements for the overcurrent protection of generators and automatic transfer switches. Article 701 covers legally required standby systems. Article 702 covers optional standby systems. When dealing with emergency, legally required, or optional standby systems, it is critical to adhere to the specific requirements outlined in these articles. These systems are designed to provide power during outages, and their reliability is paramount. Proper overcurrent protection is essential for ensuring that these systems function as intended and that the equipment they serve is protected. Consider also the concept of selective coordination. Selective coordination is a design approach that ensures that only the overcurrent device closest to a fault opens, leaving the rest of the electrical system operational. This is particularly important in critical facilities, such as hospitals, data centers, and emergency response centers, where a power outage can have serious consequences. Selective coordination can be achieved by carefully selecting and coordinating the overcurrent protective devices in the system. Time current curves, or TCCs, are graphical representations of the operating characteristics of overcurrent protective devices. TCCs show the time it takes for a device to trip at different current levels. Engineers use TCC to coordinate overcurrent protective devices and ensure that they operate selectively. Arc flash hazard analysis is another important consideration in overcurrent protection. An arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flashes can cause serious burns, injuries, and even death. An arc flash hazard analysis is a study that identifies the potential arc flash hazards in an electrical system and determines a level of protection required to mitigate those hazards. Personal protective equipment, or PPE, is used to protect workers from arc flash hazards. PPE includes items such as flame-resistant clothing, gloves, and face shields. The level of PPE required depends on the severity of the arc flash hazard. Regular maintenance and testing of overcurrent protective devices is essential for ensuring their reliability. Circuit breakers should be tested regularly to verify that they trip properly. Fuses should be inspected to ensure that they are not damaged or corroded. Infrared thermography can be used to detect hot spots in electrical equipment, which can indicate a potential overcurrent condition. Hot spots should be investigated and corrected promptly. The installation of surge protective devices, or SPDs, can help to protect electrical equipment from voltage surges caused by lightning or other events. SPD divert surge current away from sensitive equipment, preventing damage. Grounding is a critical aspect of electrical safety. A properly grounded system provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device to trip quickly and clear the fault. The grounding system should be inspected regularly to ensure that it is intact and functioning properly. Finally, remember that electrical codes and standards are constantly evolving. It is important to stay up to date on the latest requirements to ensure that your electrical system is safe and compliant. Continuing education courses and professional development opportunities can help you stay informed about changes in the electrical industry.